doing so, that's going to introduce a new mechanism. So it's called elimination. So there's two types of elimination, E2 and E1. So the 2 and the 1 refer to the kinetics, bimolecular and unimolecular. And the complicating part of this, why I divide these modules, the reagents that we see in module 5, we're going to have to now understand that they're reacting as bases. But these bases look like nucleophiles. So again, as you approach studying for the final, you're going to have to sort of know these reactivity patterns of these reagents. The final exam, again, is it's 70 questions. It's written by the American Chemical Society. In the order in which you see the problems on the exam are in any order. So it's not modules 1 and 2 and 3 and 4 and 5. You might get nomenclature, and then you might get lesson 2, and then you might get conformational analysis. So one of the challenges on that exam is you're switching context from every question. There are 70 independent questions. On my exams, I tend to write, refer back to question 2 and answer question 3. The final exam is not like that at all. In reference to that, there were some emails about question number 27 on the exam. Yesterday I regraded that. So your zip grade answers have been updated. I have not moved those scores into Canvas and updated those yet. We're coming up on Thanksgiving break, and then after that you have like 2 more classes and then the end of the semester. So sometime prior to Thanksgiving, I'll create an Excel file where I take your cumulative points so far, and then I'll create 3 columns, A, B, C. I think just by the amount of points everyone's accumulated so far, everyone's moved past an F, probably past the D, so you're probably in a C grade at this point. And the numbers in those columns will tell you how far you are away from getting a C, a B, or an A. And then you just divide that number by 3, and that's the number of questions you have to get right on the final to get that grade. The average raw score out of 70 is 20 questions, so 60 points. So if you're performing about average, you can expect 60 points from the final. So everything between now and then is really going to affect your trajectory in your final letter grade of the course. Again, the SNATMS bonus is open. That's worth 20 points to make a short video. The intent of which is you learn something, now teach it to someone else, basically. Any questions before we get started? Yeah.
When you send us that number of where we stand in the class, will that include our bonus points, or will we add them ourselves?
Yeah, the total number is what I call the required points, and then your bonuses are just added into that. So the percentages, the way I do this, the percentage is only related to the letter grade. So as long as you're filling up these point buckets, moving from F to D to C to B to A, that's really what you're concerned about, are the point cutoffs. You met that.
So I know you said you were going to send us a breakdown of like where we stand. Will that include our individual bonus points, or will we need to add them?
All the points will be added in one cell.
Thank you.
So I use the word on here, celebration. You may not think that way, but I'm a little bit older now, and you know, you've been on this journey in this class and all your other classes. So I think, you know, the journey's tough, but you need to celebrate where you've started from and where you've come from. And what you'll see in this module is it's really going to start putting all of these individual pieces together. So diagnosing the reagents, as we'll see today, conformational analysis is very important. So Newman projections, spectroscopy, because if a starting material can go to two different things, how are you differentiating them? So the uniqueness matters. And so everything we've learned so far, how to take an alkane through radical substitution to an alkyl halide. And now what we're doing is elimination. And elimination, generally speaking, is the formation of a pi bond. So for this module, it's a CC pi bond and alkene. If you go on to 256, the eliminations in there can form carbonyls. So that's been separated into that class and that module. And if you do go on, the point of organic chemistry is to make stuff. So in 256, you learn a ton of reactions, and then you learn the strategies for making complex molecules. So hopefully the class so far has given you a preview of, you know, how a drug is made. As a side note, I went to Moffitt on Tuesday with a steroid shot in the keister, and I got an antibiotic called clarithromycin. So my 256 Module 4 exam is going to be on clarithromycin and how the reactions they learned in that class can make that molecule. And if you look it up, it looks complex, but if you understand the bond disconnections, it's everything that you learn in these classes. So the point is, you know, that the science impacts health downstream. And, you know, if you're pre-professional, vet, dental, medical, whatever, I think the most powerful thing you'll have, other than being a surgeon, is your prescription pad. And so if you have an awareness of functional groups and drugs, you know where these things lie and how to prescribe them. So with that, now we're getting into the nitty-gritty details, as I said, of diagnosing reagents to understand their reactivity. And as a review, so we've talked about nucleophilicity and basicity. So basicity is really dealing with proton transfer. So that's your typical acid-base reaction. And we talked about pKa's of functional groups. So nucleophilicity is you're forming now carbon-carbon, carbon-nitrogen, carbon-oxygen bonds. So anything that forms an OH, NH, or CH, that's acid-base. And so now you have to look at those reagents and decide, is it going to be a base or is it going to be a nucleophile? For the purposes of this module, we're going to be looking at these things as bases that will do eliminations. So in terms of what we see here in blue, that's SN2. And then over in red, this is the new one, E2. And I've written them as NU with a lone pair or B with the lone pair, so nucleophile or base. We saw that for SN2, the nucleophile attacks the carbon bearing the leaving group, and that substitutes. Now with elimination, if the alpha carbon is bearing the leaving group, we're concerned now with all of the beta carbons and any hydrogens attached to them. The base is going to abstract a proton. The electrons in that sigma bond collapse to form a pi bond, and then the leaving group leaves. And what I can point out about why this is weird, in a sense, we learned that a CsP3 H bond, so for like an alkane, has an acidity of about 50 on the pKa scale. So it's not very acidic. But these bases that we learn are pretty weak bases. So if you have something that's a weak acid, you need a strong base to deprotonate it. But the arrangement of this X carbon H, that CX bond lowers that acidity quite a bit. So it's more acidic, and you can use a weaker base to do it. And we'll look at the types of bases. They're typically oxygen or nitrogen bases. But the main pattern that we're looking for here is HCCX. So those four atoms. And again, we talked about dihedral angles. So the relationship between the H and the X group is very important for understanding this mechanism. So just some nomenclature terms here. What we're concerned with is we know what the leaving groups can be. So halogens or these triflates, sulfonate esters. Now we need to evaluate the beta hydrogens. And if there's multiple beta carbons in a molecule, you can have more than one beta hydrogen. And then the question is, which one is the base going to go after? So it says here the choice is not random. And really what we're looking at is that dihedral angle. And I'll show the model today with the colored hydrogens in the leaving group to show you that it's a rational process based on everything we've learned so far. And the way that the base approaches that hydrogen will matter in that the dihedral angle of these four elements has to be anti. So just to use sort of the stick figures, and if you're looking at a Newman projection, down that bond, so that would be X, the beta carbons in back. I'm overlapping here, but so that angle has to be 180 degrees. And we'll talk about why that is using the orbitals that are involved in the elimination. So to give you the context of building up from an alkane to where we're at now, we'll start with a couple questions to put this mechanism into context. We're going to start with butane and treat it with some halogen X in the presence of heat to give some product. and it says the mass spectrum of that product has the following information. So we have the parent, M plus, and now the difference between those is 2, so M plus 2. And from our Module 2 learnings, what halogen would have been used? So what is X2 if you get this ratio of M to M plus 2? So that's going to be bromine, because you have, this would be C4H9Br would be the molecular formula of the product, but again, that bromine is 2 naturally occurring isotopes. So this would be C4H9 35, no, 79, sorry. (79) Br, and then C4H9 81 Br. So the difference in 2 comes from the 81 minus the 79. So we've established that now butane is going to form a bromobutane. And it says, what is the major product of that, knowing the selectivity of bromine? And using what we've learned, we can draw 2 constitutional isomers. So 1 bromobutane and 2 bromobutane. So from the radical CH substitution, bromine was more selective, so it should form which one as the major product? The 2 bromobutane. So again, we were evaluating the class of hydrogens, primary, secondary, tertiary. There's no tertiary, so secondary substitution is preferred. And so we'll call that now the alpha carbon. So if that is the alpha carbon as our starting point or goalpost or whatever, how many beta carbons are there? So you have to follow, like, branch off the chain. So if this is alpha, that would be beta, and then that would be beta. So there's 2, and since they're different, I'll just say this is beta, and we'll call that beta prime just to differentiate them. And now we're just counting how many are on each. We have a methyl, so that's 3. And then a methylene, so that's 2. And that gets us 5 beta hydrogens. So before I introduce the next slide, what's complicated about this is we're going to treat that with a base that's going to abstract a beta hydrogen. And the question is, there's 5 of them, so which one is the base going to go after? So what will guide us in determining the answer to that is the stability of the product that is produced. So in order to understand that, we're going to review the bonding patterns of alkenes a little bit and then talk about an addition experiment that helps us normalize the stability of alkenes. So here is the orbital description where that is your sigma bond. And then here you have your p orbitals overlapping to form the pi bond. So that overall, the sigma plus the pi is the double bond. So to fully cleave the double bond, to break the sigma and the pi bond requires 611 kilojoules of energy per mole. The sigma bond, a typical carbon-carbon sigma bond is worth 347. And so the difference between those two is 264. That's the energy to just break the pi bond. Because that's pretty strong, as we see here, look at, I'll do some coloring. So the nature of those four substituents. So in the left one, R1 and R3 are on the same side. And then on the right one, R1 and R3 are on opposite sides. So again, that's when we use the cis and trans or E and Z descriptors for that isomerism. Because that pi bond is so strong, those things will not rotate or interconvert easily. So between cis and trans constitutional isomers, one is typically going to be more stable than the other. And that's ultimately how you're going to decide which beta hydrogen is abstracted. So to just give a brief introduction of this. So if that's an alkene, if you hydrogenate it, each carbon gets a hydrogen, so that's called an addition reaction. And as we wind this semester down, after we learn how to make alkenes, we're then going to use them for other addition reactions. So this is the first one. It's called hydrogenation. And so maybe the other thing I'll write on here is plus heat. The heat is what is measured experimentally. And that is how we can then rank alkene stability. And so you rank them according to the number of carbon substituents bonded to the sp2 hybridized carbons. So if there's 4 carbons, it's tetrasubstituted. 3, it's tri. So 2 is di, but now there's 3 scenarios. Trans means the highest priority groups are on opposite sides of the pi bond. Cis, they're the same side. This new one, geminal, that means those substituents are on the same carbon. So cis and trans, they're on the two different carbons. Geminal means they're on the same carbon. And then mono substituted. So tetra is the most stable, followed by tri, then di, then mono. And as we'll see on the next slide, typically a trans substituted alkene is more stable than cis. And the reason for that is right here. When the groups are on the same side, they're closer together, and that introduces strain. So here's the general equation where you have your pi bond. You're adding the elements of H2 across that, and now you're just ending up with that sigma bond, or you're making an alkane out of the alkene. And the heat is what is measured experimentally. So on the trend here, on the left, we're starting with 1-butene monosubstituted, so it only has one carbon substituent. When you add H2 across that, you get butane, and that generates negative 126 kilojoules of energy per mole. The next three examples are the di substituted. So cis, they're on the same side. Geminal, they're attached to the same carbon. In trans, they're opposite. So there's a little bit of fudging here because this center one is not producing the same butane, right? But as you see from the cis in the trans is generating less heat. So that means the starting alkene is more stable. Then we have tri and tetra, and you see the tetra generates the least amount of heat of all of them, meaning that that bond is the most stable. So when we're looking at which beta hydrogen to eliminate, we want to choose the one that's going to generate the alkene with the most amount of carbons on it. Any questions so far? So of those four structures, which one is the most stable? We rank them. So mono, di-cis, di-geminal, and di-trans. So the di-trans will be the most stable. So we took butane, we made 2-bromo-butane. alkane. And so let me get this oriented the way I want here. So the big purple one is the bromine. Here is the beta carbon, that's methyl. And then this beta prime carbon, which is methylene, notice the hydrogens are colored different. So that is the clue that something is important about this, but not about this. So this is the model we'll use for these next couple of questions to understand, one, how you can form different constitutional isomers, and two, which hydrogens are important to form cis versus trans. So we have the elimination. It's going to be E2. I haven't talked about the base yet. We'll get into that, but some base is going to react with that to abstract a proton. And the question is asking which one of those would generate the least stable alkene. So I'll just number these 1, 2, 3, and 4. So I guess my first question is, if we can get rid of the distractor responses, which hydrogens will not be sort of in play for this reaction? So 2 and 4, because 2 is an alpha. So this was the beta, this was the beta prime, and then 4 would be gamma. So we're only concerned about the beta hydrogens. Now between 1 and 3, which one of those would generate the least substituted alkene? So maybe one way to think about it is this lasso term. When you do an elimination, you have to remove 2 things. And so if you just lasso them out and shove a pi bond where they were, you can sort of get to the product. So if we eliminate H1, so if we lasso those out and then shove a double bond between 1 and 2, that's going to generate 1 butene. And so we know that it's monosubstituted, so it's going to be the least stable. So now for this question, it's the opposite. We're going to lasso out the H at beta prime, which is carbon 3. We put the double bond in there. And now the choice is trans or cis. How do we know what we're going to form? So to put that in perspective, so from the beta carbon, the methyl group, there's 3 hydrogens, right? It does not matter which one you abstract, because that carbon 1 is still ending up with two hydrogens. So any one of those can be abstracted. But with beta prime, now it will matter because we need to achieve that 180 degrees between the H and the leading group. So the relationship between green and purple and red and purple is going to be different. So they'll give you the cis or the trans depending on the dihedral angle.
I don't want to do this. Maybe I don't want to do that.
So now with the green and the red, the question is asking you which one of those is going to get abstracted to form the trans alkene. So the red one. So to review everything we talked about so far this semester, you see that the carbon backbone, as I'm holding it as it's drawn, it's all in one plane. And so to answer this question, we really need to look at a Newman projection. So instead of looking at it this way, we're going to rotate. So it's the best way to rotate this. Maybe I'll put the hydrogen in front and the bromine back. So all I'm going to do is just rotate the perspective. I'm not rotating any bonds or anything, just how it looks. Now when you look like that, see the angle between the red and the purple? Like it's automatically 180. Now look at carbons 1 and 4. You see the relationship? So their dihedral angle is also 180. So that means when you lasso out the H and the Br, when the pi bond goes here, they're going to be trans. So if the red one does that, the green one can't do the same thing, right? It has to be different. So now I'm going to do a bond rotation to move this down and then watch what happens to this group. So it's like we learned in the Newman projections. So that's the reactive conformation for the green one. And now look at these groups. The pi bond goes there, they're now cis. So the complicating factor of this is, you learned about from the Newman projections, you generally want your methyl groups as far away as they can be, right? So if either of those H's is acidic, now you have these two conformations. So you have to evaluate the stability of those versus the stability of the product that's ultimately formed. So the reaction coordinate, as we'll see in a couple of minutes here, gets a little bit more complex. So to recap here, the red one gets deprotonated to form the trans alkene.
and then the cis one gets deprotonated, or the green one gets deprotonated to form the cis alkene. So that is really where you're going to have to put your effort into in figuring out. Again, it doesn't matter at carbon 1 because you have 3 hydrogens and you're ending up with 2 hydrogens on that carbon of the alkene. But now with these, since we need to achieve that anti-relationship, it does matter which one gets deprotonated. So in terms of this happening, so there's the anti-relationship between red and purple. So the base is going to come over here and see this hydrogen, so it'll extract it. So now I'm going to rotate it this way. The electrons in this sigma bond have to go somewhere. So that somewhere is the anti-bonding orbital of this bromine carbon bond. So there's electrons in this bond right here. Remember that for every sigma bond, there's a sigma star bond. And it's 180 degrees. So remember, for nucleophilic substitution, it has to come from that trajectory. So when you have these things aligned, these electrons go right into that orbital. That forms your pi bond, and then this leaves. So that's why you need the 180 relationship. So the different ways of drawing, again, will help you better understand the orbitals involved in this process. So the mechanism or the reaction is called dehydrohalogenation. So you're removing the elements of HX to give you an alkene. And so now this is the first slide where we're seeing this base. So it's an oxygen base. So O minus, those are called oxides, so ethoxide. And again, we know that the pKa of this alcohol is about 16. The pKa of that hydrogen is about 50. So normally you'd need a much stronger base to deprotonate that. But again, when you have this alignment of H carbon leaving group, the acidity of that beta hydrogen is much lower, or it's much more acidic. So here we have, partial bond formation between O and H. We're breaking the sigma bond, we're forming a pi bond, and then we're breaking the carbon-bromine bond. So another way of describing this is, as it's drawn, it's called an anti-elimination, and that's generally preferred. But as we'll see on tomorrow, Saturday, I'm just kidding, as we'll see on Monday, we learned about rings, right? Cyclohexane rings. Sometimes you cannot achieve 180 degrees. So you can get sin elimination, where you don't necessarily have the exact 180 relationship you need. So again, that's a complicating factor or a nuance in learning this is, anything's possible, basically. So as I said, here's the orbital description. You have that carbon H sigma bond, so those two electrons. When you have the anti-relationship between the H and the leaving group, those electrons are, the dihedral angle between those electrons and the anti-bonding orbital is 0. They're directly in line with one another. So two electrons, an empty orbital, they go right into there, and then that bond breaks. So I know I can't stress this enough. The 180, the reason that is because of those orbitals. So in the scheme shown here, because we have two different reactive conformations, we really need to look at their energies and then the energies of the products that are produced. So notice the arrow here. There's going to be some distribution of those two conformers at, room temperature or whatever. So we know from Newman projections that having the methyl group's anti is more stable. So that's why the arrow points more to that way. And when you do that elimination, you end up with a more stable product. The lesser populated conformation is where the two methyl groups are now gauche. That was the 60-degree relationship. Now that elimination leads to the cis, which is less stable. And this is sort of the ideal scenario where the more stable conformer leads to the more stable product. But that's not always the case. There'll be some reactions where of two choices, the least stable conformer will actually go to the more stable product. And that's where these reaction coordinates get a little bit more complicated. So we see that here where, notice now on this, I don't have the time axis going in one way. The time axis is sort of going in both ways that can lead to the two different products. So here are your conformers. So that's the gauche one on the left, the anti one on the right. They interconvert from more to less stable through the eclipsing interaction. So really the time split can go this way or the opposite way. So again, that's like if you're going down a hill when you're hiking and you hit that sort of fork in the road, are you going to go to the right or to the left? And those are two different time paths. So we learned that from the starting material, we have to go through a transition state, the energy of activation, the rate limiting step to get to our product, whatever that stability is relative to where we started. And the same thing for the other side. And again, how this gets complicated is understanding the populations of these conformers relative to this energy here. So that barrier, and then ultimately comparing the final energies of the products. So that is the last slide. I sort of knew I would run short on time in the sense that I don't want to introduce the next thing and leave it hanging. Because what we'll start with on Monday is, that's an acyclic system. You can map any sort of carbons on that chain, the same thing happens. On Monday, we're now going to put the H and the X into the cyclohexane ring. And now it gets more complicated because there's chair flips. Are things axial? Are they equatorial? What's the dihedral angle? How then do you determine where the alkene's going to end up? So that needs a lot more explanation. And so we'll start that fresh on Monday. And so don't forget to do your quiz. I would say do it now rather than tomorrow at 11:55 so you don't forget.